Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today we're going to do expected value or expectation. Now before we get to our main topic, expected value, we want to introduce the idea of a random variable. A random variable is a variable whose values depend on the outcomes of a random phenomenon, like say, where is my electron? Or a probability experiment, like say, rolling a die, right? So we're going to stick to random variables that are called discrete random variables, and that means that they have finitely many values, or they could have countably many possible values. Countably many or countably infinite means that there's one for each natural number, or that there is the same number as natural numbers, which is kind of a lot. There are infinitely many natural numbers, but if you literally lived forever, you could count them all, unlike, say, the real numbers, where there are so many you could not count them even if you lived literally forever. Now, in these examples, we're not going to worry about countably many possible values. We're just going to deal with examples that have finitely many possible values. So, our first example, rolling a six-sided die, a standard six-sided die that has the faces 1, 2, 3, 4, 5, and 6 on them, like a normal person. Now, we could say that x, the variable, represents just the roll of the die. So the values of x are the same as the outcomes, right? But we could say, hey, okay, now we're going to gamble on this. I'm going to wager some money on this die. Now, if I roll a 1, or a 2, or a 3, or 4, or 5, or 6, I'm going to win or lose different amounts of money, and that money will be the value of x. Okay? So if I roll a 1, I lose $1. If I roll a 2, I gain $2, etc. Right? So these are values of x, and you can see they can be positive or negative, and they can be different things, right? Importantly, even though I have 6 outcomes, I don't actually have to have 6 different values of x. I could say if I roll anything less than a 6, I lose $1, but if I roll a 6, I gain $5. Nice. So you see, there are lots of different ways that we could have values for a random variable whose values are generated by this probability experiment with just the same probability experiment, right? Same outcomes each time, but these 3 different sets of values for x mean different things. Alright, so now we're ready to do expected value. The expected value of a random variable, x, is the weighted mean average of the values of x, and the weights are given by the probabilities of those values of x. And if you don't know what weighted mean or weighted mean average means, that's okay, we have a formula for you. But if you do know what weighted mean is, then this should make a little bit of sense to you. If you would like to see how we come up with the formula and all of that stuff, we're going to stick that stuff in an appendix, a bonus video, and you can watch it there. But for now, let x1, x2, x3, etc. be the values of a random variable, and P1 and P2 and P3 be the corresponding probabilities. That means that P1 is the probability that this value of x happens, and P2 is the probability that x2 happens, and P3, you get it, right? So, given that, the expected value of the random variable x is going to be the value of x times its probability, plus the next value of x times its probability, plus the next value of x times its probability, etc., all the way up until you've used up all the possible values of x and all of their probabilities. This is the expected value formula. If you're familiar with weighted mean average, you're probably saying, don't I divide by the sum of the weights? Well, in this case, the weights were the probabilities, and the sum of the probabilities of all of the things has to be 1. That's kind of the details that we're sweeping under the rug for now and sending away to the bonus video. So let's look at some examples that aren't really word problems very much at all. Here you have a table showing the outcomes of rolling the die and the values of x. Now what we want here are the probabilities for each value of x, which can be different from the probabilities of the outcomes. And in this case, the value of x was just rolling the die. So each of these outcomes had a 1 in 6 chance of happening. So each of these has a 1 in 6 chance of happening. So here are the values of x, and here are their probabilities. So the expectation is going to be each value of x times its probability. And then you take the next value of x and you multiply it by its probability. I'm going to take this times this plus this times this plus this times this, etc. And so we get this, which can be simplified, right? First of all, you should notice that they all have a common factor of 1/6. That is the case this time, which means that we can factor it out and simplify our calculations a little bit. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is going to be 21 times 1/6, or 21/6, which reduces. They each have a common factor of 3, so what you end up with is 7/2. Or if you're doing probability, you might want to write this as 3.5. So what does expected value mean? How do we interpret this? Now, we said this is a weighted average, right? Or a weighted mean average. So we think about what that means. The expected value for this random variable tells you in the long run, if you repeat this experiment over and over, what value of x are you likely to get on average? If you were to perform this experiment 1,000 times, and the value of x in this case is just what is the dice going to tell you, or what is the die going to tell you, it's just going to tell you the average roll, the value of the average roll. So if you roll the dice 1 billion times, on average, you're going to get a numerical value of 3.5. Now, you'll never actually get a value of 3.5, but on average, in the long run, about half of your rolls will be below 3.5 and half of them will be above 3.5. So here's a very similar one, right, where we have values of x and we have their probabilities. And because each of these values is different, because this has a 1 in 6 probability, this has a 1 in 6 probability. So now when we calculate the expected value for this x, we're going to multiply these values of x by these probabilities. So we take -1 times 1/6, plus 2 times 1/6, plus -3 times 1/6, and this is going to tell us the average value of our gambling wins or losses, if we do this rolling the die and betting on it for a very long time. And just like before, you notice that each of these has a common factor, so we factor it out, rearranging the order to make it easier, we get 3 times 1/6, or 1/2. Yeah? So that, on average, with this gambling setup, you will win, in the long run, 50 cents, or half a dollar, in the long run. Now, that's not going to say that every time you do that, you're going to win 50 cents. That means that you're going to lose a lot, you're going to win a lot, but in the long run, you will earn, on average, 50 cents per roll. Now, here's this one, and this one is different in an important way. There are only 2 values of x this time. X can either be -1, you can lose $1, or you can have x equals 5, you can gain $5. This is different. It's also different because these 2 values of x don't have the same probability. There is only one way to win this $5 in this die rolling money gambling scenario. There is one way out of 6 possible die rolls to get this. But there are 5 different ways to get -1, to lose $1. So what you're going to get is you're going to get these 2 values of x, and they have different probabilities. They don't have equal probabilities this time. So you take the one value of x, -1, and you multiply it by its probability. You take the only other, in this case, value, and you multiply it by its probability. Now this time you see they don't have a common factor. We're just going to have to go through. -1 times 5/6 is -5/6, and 5 times 1/6 is 5/6. The expected value is 0. This leads us to the definition of a fair game. A fair game is a game where the expected value or expectation is 0. So this setup here is a fair game. Its expectation is 0. This here was not a fair game. Its expectation was half $1. it's weighted in the advantage of whoever plays it. So this is an important class of examples, playing games, where the values of the variable are net winnings or losses. Frequently there's going to be a cost to play, and you may win or lose, and so the term net losses means all your losses together, or net gain means I had to pay $1 to play, so the $5 I won isn't really 5 whole new dollars, only 4 of those dollars were new, 1 of them was my original dollar, right? Net win. So we're going to be figuring out what X is, right? That's a big part of each of these problems. So our first word problem. Maria is taking a multiple choice test in which there are 5 possible answers. 5 for each question. The instructions indicate she will be awarded 1 point for each correct answer and penalized 1/4 point. She will lose a point for each incorrect answer. And if she leaves it blank, she doesn't gain or lose a point. Okay? So if Maria does not know the answer, should she guess? We will use the expected value to determine the long-term, on average, boost or harm to her score if she guesses. So suppose Maria guesses on a question. Now, how many different ways can this turn out? She can be either right or wrong. She can guess correctly or incorrectly. For each of these, we want to examine the value of X, and we want to examine the probability of that thing happening. So, if she gets it right, she gets a point. Hooray! If she gets it wrong, she loses a point. Right? So these are the values of X for right and wrong. The probability of being right. Now there's 5 possible choices, and only 1 of them is correct. So this is a 1 in 5 probability. The probability of being wrong. Well, there is only 1 right answer. That means that there's 4 wrong answers. Right? So this is the kind of table we want to make, showing the different values of X and their probabilities. And now we will put this into the expected value. Expected value of X takes the value of X, multiplies by its probability. So we multiply each of these values of X by their probabilities. 1/5 minus, well, look at this, 1/4 times 4/5. Those 4's can just cancel, and you end up with 1/5 minus 1/5, which is 0. This is what we called a fair game. In other words, for this question, it actually doesn't hurt Maria to guess. It won't, in the long run, benefit her to guess either, but it doesn't hurt to guess. Let's look at the problem again with a slightly different setup. Giselle is taking a multiple choice test. It's a different test where there are 4 possible answers for each question. Giselle also gets 1 point for each correct answer, and she loses a point for incorrect answers. So the values of X end up being the same, but the probabilities are different, because if there are 4 possible answers, 1 out of 4 chance of getting the right answer and 3 out of 4 chance of getting a wrong answer changes the expected value. So if Giselle does not know the answer, should she guess? Now this time we're going to take 1 times the probability of getting the right answer, and then we're going to take negative 1/4 times the probability of getting a wrong answer. 1/4 minus 3/16. Well, you've got to get a common denominator. That's 4/16 minus 3/16, which is 1/16. This is a positive value. That means that in the long run, she will gain 1/16 of a point on average, not actually 1/16 of a point each time she guesses. This is positive. That means that she should most definitely guess. In the long run, she will gain points. Not a lot, but she will gain points by guessing. So let's do the next example. Althea Vestrit is attending the Traders' Ball. At the door, she is given a free ticket for the $75 door prize. A total of 300 tickets will be given out. Determine her expectation. Now, she didn't have to pay anything to get this door prize ticket. So, there are just a couple of outcomes. If she wins, what does she win? She wins $75. If she loses nothing. It was a free ticket. The probability of winning. If there are 300 tickets, we assume that only one of them is going to win the prize, and that the other 299 tickets will not win the prize. They will, in fact, lose. This is the important part. Once we get the expected value formula, we just plug it in, right? So we'll take the net win or loss times the probability of winning that or losing that. And then we'll take the net win or loss and we'll multiply by its probability. Now that one ends up being pretty easy. So what's 75 over 300? It's going to reduce to 1/4. That is, if she goes to 1 billion of these, she can expect to win about 1/4 each time. On average. Again, she's not actually going to get 1/4 each time she goes to this ball and gets a ticket. On average, she will get 1/4. Sometimes she gets nothing, sometimes she gets exactly $75, but in the long run, the average earnings will be 1/4. So suppose she's still at this ball, yeah? They've also got another raffle. It's not the door prize. This one, it costs money to buy a ticket. It costs $75 to buy a ticket for a chance to win a $20,000 sailboat. There are 400 of these raffle tickets. Determine the expected value for one ticket. Again, there's only a couple of options. She can win, yay, or she can lose. Sad face. Now, if she wins, she doesn't win $20,000. This is why we talked about net winnings earlier. She paid $75 to get that ticket. She didn't get 20,000 new dollars. She gets $20,000 less the $75 she paid for the ticket. She gets 19,925 new dollars. The probability of this is one winning ticket out of 400 total tickets. Losing means that if one ticket wins, 399 out of 400 are losing tickets. Sad. Now, if she doesn't win, she doesn't get her $75 back that she paid for the ticket, so she loses those $75. This is a big difference between this problem and the previous problem. In the previous problem, it didn't cost anything to lose. Now it costs something to lose, and her earnings are adjusted by the cost of buying the ticket. So these two values represent her net win or loss. Now the expected value is what happens when we take those two values of x and multiply each of them by their probability. And that doesn't look like a very good set of parentheses. Now you see that these have a common factor of 25 and these have a common factor of 25, so let's reduce each of these. And then we can multiply 3 times 399 and get 1197. And when we subtract these, we get something that's actually very nice, negative $25. It's not very nice if you're expecting to get money from playing this game. What this tells us, the negative expected value, is that on average, you're going to lose $25 every time you participate in this raffle. Sometimes you'll win a sailboat, but most of the time you're going to lose money. What this means is that this is not a fair game, that unless this game is for charity, you probably don't want to play, you're going to lose money. Probably. Our next example, second to last, is a different set of raffle tickets. We have 1,000 raffle tickets and they're sold for $1 each. One grand prize has $600 winnings, and there are 3 consolation prizes of $100. Assuming the probability, blah, 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 blah. It's not really these values, but we're going to do that to make it easier. Assuming the probability of any given ticket winning the grand prize is 1 out of 1,000, and the probability of any ticket winning a consolation prize is 3 out of 1,000, determine Penny Lane's expectation if she purchases 1 ticket. Now, we've really helped you out here by saying exactly what these probabilities are going to be, right? You don't have to worry about conditional probability, blah, 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 blah. All we need to know is what are the possible values of x and what are their probabilities. Last time, you either won or lost, right? But now, there's a grand prize and a consolation prize. But there's also the scenario where you get nothing. So you win big, win little, or win nothing, i.e. lose. If you win big, you're going to get $600, but one of those dollars was not new, you had it already, so you get $600 minus the first dollar that you put in. You get 599 new dollars. If you win small, you get $100. one of those was your dollar back, you get 99 new dollars. If you lose, you don't get anything, you lose $1. Now the probability of winning big, we said, was given to be 1 out of 1,000. And the probability of winning small, a consolation prize, was said to be 3 out of 1,000. Now if this is supposed to be probability, and it works correctly, then the probability of losing has to be what makes all of these add up to one whole. So there's a 1 in 1,000 of this, a 3 in 1,000 chance of this. There's altogether a 4 in 1,000 chance that you'll win something, which means that you'll have a 1,000 minus 4, or 996 chance out of 1,000 to win nothing. So let's do our expected value for this setup. We've got the expected value will be the net winnings for the grand prize times its probability, the net winnings for the consolation prize times its probability, and then you've got the net loss, in this case, of losing times its probability. So simplifying a little bit, we see that we need to multiply 3 times 99, and then we can add these like fractions by adding and subtracting the numerators. So we add the two positive ones, subtract the negative one, right, and we'll see that we get negative 100 out of 1,000, or, on average, negative 1/10. And I write it this way because these represented dollar values. What this says is that on average you're going to lose 10 cents. 1/10 means 10 cents out of $1, right? 1/10 of $1 that you lose on average. Again, this is a kind of raffle that you don't really want to play if it's not for charity, a good charity, presumably. Related to the concept of fair game is the idea of fair price. This is the amount that you pay that will result in an expected value of 0. So fair price equals the expected value plus the cost to play. So for our previous example, the expected value was negative 10 cents, or negative 1/10, right? And the cost to play, it cost $1 to get a ticket. So the fair price should be 90 cents, or 9/10 of $1. So let's look at this problem again, assuming that all of the probabilities are the same, but now instead of costing $1 to play, it costs 90 cents to play. If that is true, and we did our fair price calculations correctly, when we do the expected value again, we should get an expected value of 0. So x. The values of x are going to be changed. The prizes are still worth 600, 100, and 0. When you win nothing, you get 0 prize, right? But since the cost to play is now 90 cents, the fair price, we're not going to subtract a full dollar. We're going to subtract 90 cents. So $600 minus 90 cents is 599.1. And this is going to be 99.1. And this is going to be negative 0.9. And when we simplify this, we will get an expected value of 0. So changing the cost to play so that it is the fair price means that in the long run you won't lose money. Now, obviously, if you're setting up a raffle to make money or donate it to charity, you don't want to do that. But this is how fair price works. You take the expected value of the original cost to play plus the cost to play, and you add them together. That is what it should cost to get an expected value of 0, to have a fair game. Now our last example is probably going to take more time to read than it is to say. Middle ear infection, usually treated with an antibiotic. If we have two types, amoxicillin and cephalexin, they each have their own success rate and cost of treatment. This includes the total cost of the medicine, the doctor's visit, and lost work. So amoxicillin found to have a 75% success rate with this total cost. But if it did not cure the infection, it had a 25% chance of not working, right? That's the opposite of this. And then it has the total cost of this, which is a higher cost if it doesn't work. That makes sense, right? Now the other drug, The other antibiotic, cephalexin, was found to have a 90% success rate, which is better, but it costs more if it does its job. If it doesn't work, it also costs more. Which of these has the higher expected value? Which of these has the least expected cost? So this is a cool example because it doesn't involve winning or losing, but it still involves a question where we would like to know which one has a better expected value. Better in this case meaning lower, right? Normally you win money, you want it to be higher. So we'll have to create two expected values. So we'll do this table for x and for a second variable, y. If amoxicillin was a success, it cost $58.40. And we said that it had a 75% chance of success. So we'll say 0.75, or you could say 3/4, that's fine. And it had a 25% chance of failure, right? That makes sense. In which case the cost is going to be this. Now these are both positive numbers. Or if you feel like it, both negative numbers, although there's not really any point to having them both be negative numbers. They're just numbers. They're both costs, right? As long as you know that you want smaller costs, we all win. Now the cephalexin. It had a 90% success rate, which means that there's a 10% failure rate. Success, failure, with a success cost of $69.15 and a failure cost of 108 even. 108.00. So now we need to find the expected values for each of these. And each time we're just going to take the values of our variable and multiply by the probability of that happening. So we take our cost times the probability of success and the cost of failure, which is also a cost, right? Times the probability of failure. And then we do this for each variable, for each of these antibiotics. We should find that the expected value of the amoxicillin is $68.10. So if you do this to lots of patients, the average cost of amoxicillin will be $68.10. Now if you do the calculations on the cephalexin, you'll find the expected value is slightly higher at $73 and, well, it doesn't really make sense as cents, 3.5 cents, right? But the point is that in the long run, this drug has a higher expected cost. So if there's no reason not to, you probably should prescribe the amoxicillin. It will have a lower cost in the long run. It works most of the time, but if it doesn't work, it's not that big a deal. Lower expected cost. There you go. That's expected value. Our dinosaur of the day is the Pentaceratops. And this has been a Badger Bear production of the wonderful world of math. Farewell, programs.